Welcome back, guys, to our level up series. In the level up series, let us see our today's question. Our today's question says critical connections in a network. Let me explain you the question in short. What does the question means? We need to return all the critical connections present in a network. Now, what is the network? You all know about the knowledge of graph. So what we are going to do, we are going to consider these all nodes as servers and these edges as the connections. So what we need to do is we need to return all the connection. What do we mean by critical connection? A critical connection is a connection which, if removed, will make some servers unable to reach some other server. So these edges are considered as the connections. These nodes are considered as the servers. So if I remove any of the connection, if the servers become unreachable, then that connection is referred to as a critical connection. Let us further understand it. See, if I remove this particular connection connecting 1 and 2, will the servers become unreached? No, because I can still reach 2 via this path, 1 to 0, 0 to 2. So if I remove this particular connection 1 to 2, then also I can reach the servers. It means this connection is not a critical connection. Let us see this connection connecting 1 and 0. If I remove this connection, will the servers become unreachable? No. I can still reach 0 via 1 to 2, 2 to 0. It means this is also not a critical connection. 2 to 0, let us see. If I remove this particular connection 2 to connecting 2 and 0, will the servers become unreachable? No. I can still reach via 2 to 1 and then 1 to 0. So this is also not a critical connection. Let us see this particular connection connecting 1 and 3. If I remove this connection, can I reach no server 3? Now the server 3 becomes unreachable. I cannot reach server 3 from any of the path. So it means this particular connection connecting 1 and 3 is a critical connection. If by removing any of the connection, my graph turns out into multiple components, it means more than one component. It means that particular connection is a critical connection. So I can clearly see if I remove this particular connection, my graph will be broken up into more than one component. It means this particular connection is a critical connection. And after removing this connection, I cannot reach the server 3 becomes unreachable. So I need to return all the critical connections present in the graph. In this case, there is only one connection connecting 1 and 3. So I will remove this. I will return this particular connection. That is 1, 3. We can return either 1, 3 or 3, 1. Both are acceptable. So I hope the question is clear to you all. We are given with the servers. We are given with the connections. We need to return all the critical connection. What do I mean by critical connection? If that particular connection is removed and the server becomes unreachable, then that particular connection is referred to as a critical connection. So the question is clear. The statement of the question is clear to everyone who is watching this video now. Now let us look at the approach of this particular question. What we are going to do is we are going to apply the DFS algorithm, but with some modifications. What are those modifications going to be? We are going to consider two more arrays. The very first array is going to be the time of insertion array, and the second one is going to be the lowest time of insertion. What do I mean by time of insertion? Just listen me carefully. The time of insertion means the time when a particular node is visited is called its time of insertion. And what do I mean by lowest time of insertion? The lowest time of insertion means if I will visit the current node, then I will refer to all of its adjacent nodes. Suppose this is a node 0, then I will refer to all of its adjacent nodes like 2, 1, but apart from the parent. And I will take the lowest time of insertion amongst these all nodes. I hope this is not much clear to you all, I know. So for that, let us look at this particular image. This will give you a better understanding. I will explain you. Suppose we are starting from the node 0. So since we are starting from the node 0, its time of insertion is also 0 and its lowest time of insertion is also 0. Then we will go to node 1, which is connecting. We have started from node 0. Now we are going to go to node 1. Consider the time of insertion of node 0 as 0 and the lowest time of insertion will also be 0. Now I have gone to node 1. So its time of insertion will be 1. Its lowest time of insertion will be 1. Just listen carefully, you will understand it. Then I will go to node 2. its time of insertion is going to be 2 and its lowest time of insertion is also going to be 2. Now go to the node 3. Its time of insertion is going to be 3 as well as its lowest time of insertion will be 3. Now I will go to node 4. Its time of insertion is 4 and its lowest time of insertion is also 4. Now see, from node 4, can I go to any other node? No, I cannot. So what I will do is, its time of insertion is 4, its lowest time of insertion is also 4. Now I will try to update its lowest time of insertion. What is the condition for the lowest time of insertion? I will go to all of its adjacent nodes apart from the parent. So what are the adjacent nodes of 4? There is only one adjacent node, that is 3. But 3 is also a parent. So I will not go to 3. So it means its lowest time of insertion will remain 4. Now I cannot visit anywhere else. Now I will compare. What is the time of insertion of its parent node? The time of insertion is 3. What is the lowest time of insertion of the current node? That is 4. It's 4. Since 4 is greater than 3, if lowest time of insertion of current node is greater than the time of insertion of the parent node, it means that particular connection is a critical connection. What is the time of insertion of parent node? It is 3. What is the time of lowest time of insertion of the current node? It is 4. 4 is greater than 3. It means this particular connection is a critical connection. You can also clearly see if I remove this particular connection, then the server 4 will become unreachable. So this is a critical connection. But with the help of a code, the approach is going to be, we are going to compare the lowest time of insertion of the current node and the time of insertion of the parent node. If the time of insertion of the parent node is lesser than the lowest time of insertion of the current node, it means that particular connection is a critical connection. So this particular connection comes out to be a critical connection. Now from 3, I cannot visit to any other node, right? So I will go to all its adjacent nodes. Is there any adjacent node of 3? Yes, it is 4 and it is 2. What is the lowest time of insertion of 4? It's 4. But 3, what is the lowest time of insertion of 3? It's 3. So 3 is already lesser than 4. So I need not to update it. Then I will go to adjacent node 2. The node 2 is the parent node, so I cannot visit it. So now I will compare. What was the time of insertion of node 2? It was 2. What was the lowest time of insertion of node 3? It was 3. 2 is lesser than 3. It means it means it is a critical connection because the time of insertion of the parent node is lesser than the lowest time of insertion of the current node. It means that particular connection is a critical connection. We can clearly see if I remove this particular connection, the server 3 will become unreachable, right? So this is a critical connection. Now I hope you all are getting. I will explain you the entire image and it will be much more clear. Now from 2, I'll go to 5. The last node which I visited was 4 and its time of insertion was 4. So the time of insertion of 5 becomes 5, lowest time of insertion becomes 5. From 5, I go to 6. The time of insertion will become 6, lowest time of insertion becomes 6. From 6 to 7, the time of insertion becomes 7 and the lowest time of insertion also becomes 7. From 7 to 8, time of insertion becomes 8, lowest time of insertion will also becomes 8. Now a new concept. See, from 8, time of insertion is 8, lowest time of insertion is 8. I will visit to all its adjacent nodes. What are the adjacent nodes of 8? It's 5 and 7. Consider these edges as undirected. Don't consider them as directed because in the question undirected is mentioned. So I'm explaining you in that context. So what are the adjacent nodes of 8? It's 5 and 7. I will go to 5. What was the lowest time of insertion of 5? It was 5, right? It was 5, 5. Time of insertion was also 5. Lowest time of insertion was also 5. What is the lowest time of insertion of 8? It is 8. 5 is better than 8, right? So its lowest time of insertion will become 5. Then I'll go to 7. 7 is the parent node of 8, so I cannot visit it, right? So now I will compare. What is the lowest time of insertion of 8? The lowest time of insertion of 8 is 5. What is the time of insertion of 7? It is 7. 7 is lesser than 5? No. It means the condition becomes false. It means this connection is not a critical connection, connecting 7 and 8. If it is not a critical connection, I will update my minimum time of insertion, that is lowest time of insertion. So what is the lowest time of insertion now becomes? It becomes 5. I will from 7, I'll go to its adjacent node, I'll go to 8. Its lowest time of insertion was 5. Its lowest time of insertion was 7. I will the lowest time of insertion of 7 will get updated and it will become 5. I'll go to 6. 6 is its parent node, so the comparison will take place. Time of insertion of 6 is, what is the time of insertion of 6? It was 6. Lowest time of insertion of 7 was 5. So is a 6 lesser than 5? No, condition becomes false. It means this is also not a critical connection. So from 6, now I will go to its adjacent node. Its adjacent node is 7 and 5. The lowest time of insertion of 7 was 5. So it will get updated. So now lowest time of insertion of 6 also becomes 5. 6 will not go to 5 because 5 is its parent node. Comparison will take place. Time of insertion of 5 is 5. Lowest time of insertion of 6 is 5. Is 5 lesser than 5? No. It means this is also not a critical connection. Now from 5, I cannot go to any other. I will just go to its parent node now. What is the parent node of 5? Parent node of 5 is 2. What was the time of insertion of 2? It was 2. What is the lowest time of insertion of 5? It is 5. 2 is lesser than 5? Yes, 2 is lesser than 5. The condition becomes true. So it means this particular connection comes out to be a critical connection. You can clearly see if I remove this particular connection, I cannot reach the node 5, 6, 7, 8 now from the server. So it means this connection is a critical connection. So now this is over. Now from 2, I will go to, I cannot go any further. So I'll go from 2, I'll go to 1. What is the lowest time of insertion of 1? It was 1 only. So it will get updated. And from 1, it will go to 0. 0 is it is parent. So the lowest time of insertion becomes 2, and these are, and the similar way when we will compare, these will not come out to be a critical connection. So what we will do at the end, we will return these critical connections which are to connecting 2 and 5, which are connecting 2 and 3, and which are connecting 3 and 4. So I hope now it is clear what do we mean by time of insertion and lowest time of insertion and how we are applying it. This is also referred to as a Tarzan's algorithm to identify. Now let us look at the, we have just applied this particular thing. First of all, we have constructed the adjacency list for which we do in almost each and every question of graphs. So you all are aware of with that. We have made one counter variable to store the time. And initially I have made it as 1. In the image, we have done it with 0. But here we have made it with 1. We can start with 1 to whatever we want. There will be no changes. Then we have made one vector v as well as 2 arrays v1 and v2. What are these 2 arrays doing? But v1 is storing the time of insertion and v2 is storing the lowest time of insertion. We have also made one vector answer to store all the critical connections. After that, we have called the DFS algorithm. What is happening in the DFS algorithm? V at the index of I equals to 1. What does it mean? It is the for the visited array. We always make visited array, right? When we use DFS algorithm. V1 at the index of I equal to counter. V2 at the index of I equal to counter. This is storing the time of insertion. It is storing the lowest time of insertion. Then I am incrementing the value of counter. I am referring to all its adjacent nodes, and I am calling the DFS for that particular algorithm. If it is already visited, if V at the index of I, right, if this condition is true, it means that particular connection is already visited. So what will I do? I'll compare. What will I do if it is already visited and it is not equal to parent? If IT double equals to parent, I'm just doing continue. If it is not equal to parent, the lowest time of insertion is getting updated, which we were doing, right? By referring to all its adjacent nodes. Else, we will compare. If V1 at the index of IT is greater than V2 at the index of I, what does it mean? If the lowest time of insertion is greater than the time of insertion, it means it's a critical connection and I am pushing back into my answer vector. So this is the approach which we have followed to get all the critical connections present in our graph. So I hope the question is clear to you all. The question was a bit tricky because we are using 2 more arrays, time of insertion and lowest time of insertion. But if you have referred to that particular image which I have shown you, then the concept of time of insertion as well as the lowest time of insertion will be clear to you all. In case the question is clear, don't forget to subscribe to our channel and share it with your friends. Thank you.